So some of the topics that we're going to cover today, he, my colleague in oil and gas, did an excellent job in terms of oversight of SNC, so I will breeze over that a little bit. The Centre of Excellence is certainly where I'll hand over to Ramy. As Ramy says, there's an awful lot of experience in that group. Some of us go back as much as 40 years, so that's a lot of HVDC knowledge over a period of time. We'll then talk about a couple of interesting HVDC projects, interlinks between Canada and the US, dynamic reserve sharing applications, and a potential vision for the future which involves HVDC. So just a little bit about our company. We are an international leader. We're an ENC organisation. We do basically everything soup to nuts, as you've seen before, guys in oil and gas. I'm in transmission and distribution. We perform EPC, EPCM, or any mix of that. The only thing we don't do directly of any size is actually construction. We look to team with constructors for those applications, and certainly we've done that on many large transmission projects. So in terms of E&R ranking, we're slowly pushing up. In 12 we're ranked number 9, in 13 we're ranked number 7. As Guy touched on before, we're a tad over 34,000 employees currently and operate in numerous countries. Just in terms of revenues, we set out about 8 billion. I think the interesting fact for me is that T&D, which is my division I represent, actually stands for about 10%. It's a little bit more than that. So through our books last year, in transmission projects, both in the US and Canada, we passed the 1 billion mark. So that's quite a milestone for us. Just a little bit in terms of where we fit, you'll see the asterisks at the top there under power. So within power we have hydroelectric, we have nuclear, thermal, transmission and distribution. And there's a really interesting one there called Altalink, which is in fact a transmission facility owner and operator. And Altalink currently owns and operates about 12,000 miles of 230 kV and 500 kV systems in Canada, and in particular in Alberta. And we've got some ambitions with Altalink, joining our division in terms of what we're looking at for projects to develop, potentially in the US, so I'm hoping that we've got a good opportunity to touch base with some of you tomorrow, particularly in the D&T sector, because we do think there's excellent opportunities here, and particularly in Wyoming. So transmission and distribution, we actually consist of 2,000 or so full-time T&D professionals, and they are T&D only, so that's kind of their lifeblood. They do that day in, day out, nothing else. So we've got quite a big band of folk, and the majority of those individuals sit very much within North America. So a little bit of a look on Centres of Excellence. As you can see in Canada, it's pretty much there. These are the main offices from west to east, from Vancouver over to St. John's in Newfoundland. In the US, we've got a number of T&D offices in Rochester, Binghamton, Pittsburgh, Augusta. And interestingly, just recently we've opened one up in Boston, and that's to do with the potential for transmission hardening on the East Coast, which is as a result of, no great surprise, Hurricane Sandy and other such events. In Houston, we've set up a small T&D operation in Houston also. Vince is actually down developing some of those opportunities with Encore, potentially with ERCOT. We also acquired an engineering house down in Rio de Janeiro about 2 years ago, and the reason why we acquired that engineering house was they had a real amount of HVDC expertise and also EHV expertise, which was complementary to our skill sets. So it's quite a broad patch, and hopefully we can do something in the middle there, in the Midwest. That's what we need to look at as well. So just a couple of shots on maybe three significant programs that we're looking after currently. One is within the Iberdrola, which is in the northeast US. For that program, we actually run, or rather oversee, an ECD, electric capital delivery budget of about $1 billion between Rochester Gas Electric, New York State Electric and Gas, and also Central Maine Power. So we pretty much provide a wide range of services. from project management, conceptual engineering, all the way through to assisting procurement, logistics, programming, rolling up consolidated financial reports, etc. So it's a pretty inclusive program, including construction support and commissioning. BC Hydro, another client that we've been working for probably for nearly 10 years now. So we signed another agreement with BC Hydro about 2 years ago. And that's a combination of cost plus potential EPC and maybe target cost contracting. Actually, it's more than 5 years. It's 5 plus a potential 2 and a potential 2. So we have a good relationship with BC Hydro. And lastly, coming out right now in Alberta, currently it's sitting at about 3 billion capital projects that we've developed over the last 5 years in transmission alone. And that's based on a 10-year sole source agreement that we have with Altalink. And that runs through a number of turnkey EPC major infrastructure additions. Again, a combination of 230, 240 and 500 kV transmission build-outs. And that's going to run for about there's another significant 4 to 6 billion to actually be invested in transmission in Alberta. So some really heavy build transmission work going on there right now. Hvdc transmission, an SNC Lavalin Centre of Excellence. So on that one, I think I'm going to hand over to Ramy.
Okay, so moving right on to HVDC, I realize everybody in the room may not be a transmission engineer, so just quickly, HVDC is the transmission of power through direct current rather than alternating current, the way it is done in most places in the world. So what it involves is just having a converter at each end to convert AC to DC, transmit it, and then put it back into AC on the other side. Looking at the Center of Excellence team and structure, so and I'll refer to this back when we talk about the projects. It has to start with a set of system definition studies where you define the voltage of the DC, how it will interface with the AC network, what type of power you're transmitting, how you will control it, what type of technology we're going to use in terms of power electronics, etc. There is a detailed design phase where you're going to look at the way that you're going to get your current to return, the way you're going to run your installation, SCADA telecommunications, building layouts. There can be cables if you're going underground or under the sea in direct current. And then we'll go and do it as EPCM, at least for the converter stations. The lines, the SNC Lavalin can go EPC on the lines. The converter stations, there are a few companies specialized in the world building those, and so we'll do the supervision, and we'll supervise the commissioning and turnover, make sure that the installation really does what it was intended to do. So why would we transmit through DC? Well, in DC there is no reactive power, so essentially you can transmit over very long distances. You don't need any intermediate substations, you don't need any compensation. So when it becomes, for large amounts of power and long distances, it becomes more economic to transmit power on direct current rather than alternating current. There are also other advantages. It works very well with cables because cables are like huge capacitors. So when you send AC through them, eventually you're going to need to compensate on the other side, and that limits the distance that you can send through cables. Asynchronous interconnections, so it's a firewall between the two sides. If you have a disturbance on one side, it's not necessarily going to reach the other side. Power flow control, so you decide how much power you send or how much power you receive, the direction and the amount of power, which under other circumstances in an AC network is not necessarily something you can control. It depends on the voltage at each end and the state of the network. And because you can carry very large amounts of power, it can also relieve congestion. In particular, if we look at Wyoming, there's a lot of potential for very high levels of generation, much higher than the amount of local load that you have in the States, which means Wyoming is a good place to export power, and especially with the large wind potential there is. And when you're going to export power over long distances, whether it's through the west or through the south or the east, then HVDC becomes a very interesting technology to use to transmit all that power. There are two main technologies for HVDC. What we call classic and what we call VSC, means voltage source converters. This is a technology that is still evolving. The maximum power being announced by the builders of converters right now is around 1,000 megawatts, although I haven't seen an actual project commissioned with 1,000 megawatts yet. The maximum capacity with classic HVDC is much higher, several thousand megawatts. You can actually build several bipoles, you can go quite high. The losses are still a bit lower, but this technology is evolving and it's coming down. Compatibility with weak networks is important. SCR here means short circuit ratio. It's the ratio of the megawatts of the converter to the fault level of the network. So if, for example, you're building large amounts of wind, wind does not contribute to the fault level in the network, so it doesn't add inertia to the network. It's not a rotating machine. So in particular, you may have places where you're connecting it and the fault level is not that high. If you want to put HVDC, you may be better off going with this technology right here. Black start. So if there's a blackout and you want to help a network get back on its feet, HVDC through voltage source converter will help get the network back online, which you cannot do with classic HVDC. You need voltage on both sides of the converter to make it work. Land requirements is often the one that decides, lower by up to 40%. It's a more compact type of installation. Multi-terminal application is quite an important one. Classic HVDC has been done with 3 terminals at most because it's exponentially more complicated as you add terminals. With the other technology, you can go multi-terminal. Why is this important? I've put here maybe preferred for renewables. This is just a rule of thumb. If you want to mitigate variability, for example, of wind or of solar or etc., then if you connect these things into a multi-terminal DC network with various sources of wind or other type of generation, then that's a way of mitigating the variability if one site drops in power, the other one may not. End user confidence, much higher here because this is still new, quite simply. The cost, as with every technology that's involving, the cost is still higher over here. O&M is supposedly lower, but we have to wait a bit longer to get some actual data. So looking at the Canada and Canada-US links, so this is by no means an exhaustive list. There are, I'm probably missing a few other converters in there, but those are the main ones. There are many other AC links between the US and Canada everywhere. Obviously, this is only HVDC. Just a word about those. The ones in red are the ones that our company is involved in. Western Alberta Transmission Link is this one right here. At this stage, it's currently, we're at the stage where we're starting the building of the converter stations and the lines. So we're in an EPC contractual position. There's a future stage where there will be a third terminal into Montana that will inject up to 4,000 megawatts. Eastern Alberta Transmission Link is right here, just parallel. Labrador Island is the one right here sending power from the Muskrat Falls hydro installation, which SNC is currently working on, and also on the DC interconnection here. There is the maritime link that will come afterwards that will link Newfoundland down to Nova Scotia, and then through New Brunswick there will be an interconnection. This will probably be AC into New England. We're talking about roughly about 1,000 megawatts, I believe. The Quebec-New England link, this was the first 3 terminal that was commissioned. It's taking power from the hydro station at Radisson. I believe it's up to 2,000 megawatts. It connects close to Montreal right here, and then it goes close to Boston and feeds into the United States. Then there are Nelson River bipoles 1, 2, and 3. There's a huge amount of power coming here down from Hudson Bay, down through Manitoba to the south. And I believe there are a number of AC interconnections also in the States here. There are 3 little dots here because number 3 is under design and it will go into construction in the next few years. Vancouver Island, 1 and 2 is here, just DC that links underwater, British Columbia to Vancouver Island. Just jumping here, Seabreeze HVDC is right next to it. It will connect British Columbia through to Washington State. And this is still in the planning stage. It's not being implemented yet. The Levy de-icer is an interesting one. It's connected just here. It's not to transmit power as such, but it's a DC converter to de-ice lines. So if there's ice accumulation on the lines, it can be up to 735 kV lines. Just take the line out of service, connect to the converter on one side, short out the 3 phases on the other side, and start injecting DC through one phase and get it back through the other 2. And you de-ice one phase at a time, you get the ice to melt that way, and then just put the line back in service. It's been built at a place where it's a hub with many different lines, and so it can de-ice, you can connect it to a number of different lines to de-ice them. Now, obviously, we don't have ice all year round. I know some people think we live in igloos up there, but that's actually not the case. So what does it do when there is no ice? Well, you need to make it useful for something, so there's a little set of switches in there that transform the DC converter into an SVC, static var compensator. So when there's no ice, it just compensates the network, injects megavars. And when there is, it just switches around and gets to de-ice the lines. Because it connects to some large lines that go up north, down south, there were some issues with geomagnetic currents as well that had to be studied. There are some other interesting issues because you want to actually create heat through the lines. Heat is losses, and every engineer has been trained since birth to minimize losses. Well, in this project, we want to maximize losses. We actually want things to heat up. So every standard that's based on minimizing losses was no longer applicable. Every calculation we're used to doing, it's all based on minimizing losses. That doesn't work either. So we had to get a team of engineers to think exactly the opposite as they would normally do, which was quite interesting. There are a number of back-to-backs here. Finally, Lake Area Power is in the planning stage, and we just started working on this one. It links Ontario down into Pennsylvania, and it goes under the lake right here, so it will be a cable, I believe, is just under 100 miles long. So going more in depth, just showing the projects that we are currently building. Western Alberta Transmission Line, or WATL. It's an ongoing full EPC that we're doing, so 320 kilometers of 500 kV line with metallic return. Right now we're building it as a monopole, so this is called stage 1, so just 1,000 megawatts. Monopole means one converter station at each end. However, the line we're building for 4,000 megawatts, so the line is already built for final capacity. There are substations at each end, which also have to be, on one side it has to be upgraded, and on the other side it's a brand new substation. So where are we at? The studies and the engineering are mostly completed. The procurement and the testing of major equipment is in progress. Next month will be dynamic performance testing, so we'll test that the control system actually transmits power the way it should and reacts the way it should. And the site is being prepared. The first transformer reached the site, I think, last week. There were a number of challenges. Firstly, the control strategy. There's another parallel DC scheme here, and there are many AC lines here on the same corridor. So what does that do? Well, if you send power through the DC line, because you can control the amount of power, you want to make sure the power doesn't loop and come back up the other side, otherwise it's useless. Other things is induction. So you have AC getting induced onto the DC line. And when that crosses through the converter, it becomes DC on the AC network and will saturate transformers. There are also harmonics that can get induced onto the AC network. Alberta is a big producer of oil and gas, so you have a number of pipelines in there. So there's pipeline induction problems that are there, and we had to study and design some mitigation measures on the pipelines. Subsynchronous torsional interactions. Well, you have a lot of generation up here near Edmonton, and DC converter control systems can sometimes resonate with the generator. So a mechanical vibration in the shaft of the generator can get translated into an electrical oscillation. The DC converter will try to compensate. By doing that, it will amplify the mechanical vibration in the generator. It ends up resonating, and you can actually cause a physical break in the shaft of the generator, and it's very expensive. And these are very complex studies to make sure that this doesn't happen, because it involves a lot of money to fix. Then another challenge is the provision for 3-terminal. Montana is right down here, and if at a later stage we're going to be extending this down, then we need to think right away of what type of switching and what type of installations we'll need there, and make sure the space is available, etc. And finally, as with every project, right-of-way and environmental permits was a major challenge, not for us, but more for Altalink, who was taking care of that part. One example is the decision to have a metallic return on the line through a third conductor rather than having electrodes. You can sometimes get the current to return through the ground, and the soil was perfect for an electrode, but it involved getting a separate permitting process for the electrodes. So it was just easier to get another conductor and return it through there. I was listening to the presentations today about all the CO2 and the gases, etc. It would be interesting at some point if somebody were to study what effect it has on the ground resistivity. I think CO2 is an electrical insulator. So if you have electrical installations in Wyoming, and over, say, the course of 50 years, the ground resistivity increases even locally because of increased CO2, then what will that do to the electrical installations? Will it worsen the pipeline mitigation effects? Will it worsen the grounding or make it harder to ground the substations? What other consequences there will be, I think would be interesting to look at that. This is just a side note. So just as a summary, we're building the monopole right now. Metallic return here, so current goes out and back in Calgary to Edmonton. Stage 2 will make it a bipole, so it will become redundant. Stage 3 becomes 2,000 megawatts. Here, 3,000 megawatts, we're adding parallel converters. And finally, stage 4, multi-terminal, where we connect down into the USA here. So we have to get every provision in building these two installations, make every provision right now at this stage to move into that stage later. When will that happen? I think the date is not fixed yet. It depends on many things. Maybe it'll be for our children's generation, or maybe for us a bit later, who knows. So this is just a picture of the first transformer arriving at site. I'll be interested to know there's very little snow there. I think it was just cold. So the next project that is right now that our company is working on is the Labrador Island transmission link. There's basically a new hydro plant here at Musqueam Falls, which our hydro division is working on, and then our T&D group is working on the DC interconnection into Newfoundland, right here all the way to Soldiers Pond. So this will be DC with a little cable going under the sea. Through the AC network of Newfoundland, power will eventually end up here through the Maritime link, another DC link, which is likely to be a voltage source converter, so the other technology. Here is going to be classic, which will reach Nova Scotia, and then through the existing AC transmission lines will feed through to New England. At the same time, the same installation connects through to the Hydro-Quebec network at the 735 kV lines, and will also eventually reach down to Montreal, Ottawa, the Ontario, and into New England as well. It's interesting to see that in Canada, most of the transmission lines go north to south, and then into the United States rather than east-west. So more provinces are connected. We want to make sure that the US is well powered rather than building east-west transmission lines between provinces. So where are we at on this project? So obviously it's a huge project between the hydro installation and the T&D. We're talking about $6 billion. We're the engineering providers for phase 1, so Labrador to Newfoundland. We're looking after the hydro project, the AC and the DC lines. We're doing all the studies we're planning for the submarine cables, but this is actually, the cable itself is actually not in our scope. Air insulated substations, 230, 315, and 735 kV, 2 DC converter stations, cable transition stations, synchronous condensers. We needed to put those on the Soldiers Pond side because the network was too weak to be able to accommodate a DC converter. It's also the reason why the other one was chosen to be a voltage source converter. It's more compatible with weak networks. So these here synchronous condensers actually add to the inertia of the network, allowing it to sustain the VAR exchange with the converter. The engineering is nearing completion. The converter station procurement is in progress. I think the team over there is doing bid evaluation just as we speak. The main challenges here, obviously coordination of all the components. So this is a team of several hundred people that we've put over there, experts in hydro, experts in transmission lines, experts in substations. And as you know, when you put many experts, each one of them thinks he's right. And so coordinating all the components can be a challenge. I mentioned the weak network at Soldiers Pond. This was a challenge during the studies. The studies are over now, and we took the measures to mitigate for that. there's going to be control coordination with the maritime link. So you have a DC here setting a certain amount of power, another one setting another amount of power there going down. So if this one is set at, say, 300 megawatts, and this one is set to export 500 megawatts, where's the difference going to come from? Are we going to bring down the whole system in Newfoundland? It's not a very big system. So the two control systems are going to have to be linked, and there are going to be some, some way to make sure that the settings are compatible. Because on a DC converter, if you ask to send 300 megawatts, it'll send 300 megawatts no matter what. If it brings down your voltage and your frequency, that's what will happen. And finally, the environmental conditions. So this is a very windy place, very icy place. There's ice accumulation on the insulators, on the conductors, and the design of the lines has to take that into account. Just a final word on another project that applied Hvdc with dynamic reserve sharing. I mentioned this in there as it may be of interest when looking at DC interconnection across states or across large territories. Hvdc is often selected because it's a firewall between the two networks. So if the frequency drops on one side or there's a problem, you don't see it on the other side. And the disturbance is not transferred. But what it means is that in the meantime, if you are importing power from someplace and something happens there, well, your DC will keep importing the power, and you'll actually contribute to bringing down the other network. So there's no assistance to a network that's in distress. All you can do is just stop the DC, stop sending power, and wait until the other side recovers. And it does not reduce the primary spinning reserve levels. So you can have a huge converter sending you 1,000, 2,000 megawatts. If the converter trips, then you still need to have your reserve to compensate for that amount of power you were importing. So we asked the question, can a DC interconnection be controlled as a generator? Can it look like a generator on the network rather than a DC converter? Can it give you automatic emergency assistance? It would partly sacrifice this firewall feature, but only partly. What are the economic benefits? Well, it would have to be justified on the basis that you can now reduce the reserves that you keep, spinning reserves. So how does it trigger? How does it work? I'm just going to explain it in the context of this project that we just finished a couple of years ago. It's an interconnection between 6 countries, Kuwait, Saudi Arabia, Bahrain, Qatar, UAE, and Oman. 400 kV AC lines here and a cable to Bahrain. And because this is 60 hertz in Saudi Arabia and 50 hertz everywhere else, you need DC converters right here to transfer between the two frequencies. So there's 1,200 megawatts of DC converter right there. And the idea of this whole interconnection economically is based on the fact that the countries can reduce their amount of spinning reserves and thereby saving money, and the cost of the avoided generation that they don't have to build justifies the interconnection. Now in the case of the DC here, there's an application which was the dynamic reserve sharing, where we had the DC react automatically if there is loss of generation on one side. It automatically transfers power to help a network recover. So how do we do it? Basically, the converter monitors the voltage, checks for a voltage drop, and it monitors the frequency, calculates the dV by dt, dF by dt, and the network studies had to find out what was the corresponding triggers for stopping whatever the converter is doing, power sales or whatever, and start trying to help. So it's determined that the network was in distress and trying to help it. So these studies, the converters were contracted to Areva T&D, now Alstom, and SNC Lavalin had prepared all of the framework for the project, the specifications, and we were helping commission and supervising the design. So the setup is you deblock the first 600 megawatts once you trigger, and then you monitor the frequency and you try to adjust the power level. If you need to deblock the other 600, you can do that depending how the frequency evolves. It overrides any ongoing power sales. So if you were selling 600 megawatts and you suddenly lose generation, you just stop selling those 600 megawatts right away and you start receiving power instead to make sure your network recovers. And obviously any other performance requirements like harmonics, etc. are temporarily overridden. So just an example, a huge loss, say on the 50 hertz side you lose 2,400 megawatts, so that's a complete installation. Under normal circumstances, the whole country would go blackout. So this is an example where you lose this in Kuwait. So the whole country will go blackout. With this installation now, what will happen is the frequency will start dropping. Eventually you reach the trigger, so pole 1, the Hvdc automatically turns on, goes to its maximum of about 600 megawatts. You can start seeing the frequency recovering here. So it tries to pull back a little bit, the frequency keeps dropping, so it comes back up, it monitors. Eventually it determines that you need the other pole to also deblock to another about 400 megawatts here, and the frequency recovers. Now, the donating network suddenly had to give 600 and then about 1,000 megawatts. So that affected them. The frequency in the donating network only dropped by 0.1 hertz. So that would be Saudi Arabia donating here, so they're at 60, they're at 59.9. No big deal. But for the receiving end, they avoided a blackout. Their frequency dropped by about 0.5 hertz, so down to about 49.5. Maybe they had some load shedding going on as well, but in the meantime they recovered. So the difficulties in this is how often do you need to update the trigger points? The networks evolve, and the trigger points may change. There's no room for error or tweaking. This is based on simulation, but we're not going to try and actually put 2400 megawatts out of service just to check if it works. So it's the day that there's a disaster that we know if it works. There's been some small problems on each side, and it has worked in the past couple of years, but it hasn't saved anybody from blackout yet because there hasn't been any blackout events yet. Both sides have to be very close in their cooperation, and if the above is taken care of, then you can revise the generation plan and you can achieve the economic benefits. So just to conclude, vision for the future. Found this little quote in Physics Today: if US states that have significant renewable resources are to export their power to more populated states, the US should build a high voltage direct current grid. Which is very true. A lot of people have seen this map. This is the wind in the US, and you can see that it's concentrated a lot towards the center. It's a similar map in Canada, and it's hard to find places where there is no wind in Canada. That's why we're all freezing. So there's a lot of potential for renewables. How will that happen? Well, we need to link different types of generation to mitigate the variability. I think we can't think of these things as isolated grids anymore. There are enough interconnections that we should look at it as a continental grid, US and Canada together. It's linked absolutely everywhere. Integration of renewables. One thing we know is we'll need multi-terminal HVDC for sure. We need multiple sources of input and output of power. We'll need both technologies. We may need dynamic reserve sharing if we can justify interconnections on the basis of reducing reserves. And so probably we'll need both LCC and VSC, probably in different layers of a DC network, bulk transfers in classic HVDC, where there's a weaker network or renewables. We might want to go more towards voltage source converter. For sure, there's huge potential for this technology in the US and Canada. Thank you very much. Are there any questions?